algorithm is to remind you about the division process. Now, depending on what generation you grew up in, you may have learned a different algorithm for division, or what country you're from, you may have learned a different algorithm. Most people learned division or copied division when they were somewhere between 9 and 10 years old, but didn't have the foggiest idea what they were doing. They were just mimicking the steps that the teacher showed them. And part of the problem with our division algorithm is that we lose track of the place value. So a lot of students could do this and they could get an answer like 7 or 701 or whatever, and they wouldn't even have a sense that their answer was wrong. So most of you are able to do this today. I'm not going to go through it. You got the answer of 71, and you had when you did the process, you had a remainder 6 here. And what that tells you is that 11 is not a factor of 787. 11 is not a factor. And the reason it's not a factor of 787 is because you have a remainder different than 0. If 0 was the remainder, then 11 would be a factor. And today, our whole goal of today is, instead of working with division of numbers, we're going to be looking at dividing polynomials. And we're trying to find out what the factors of the polynomials are, because the factors tell us where the zeros are, and it tells us where our x-intercepts are. So it's going to help us with graphing these polynomial functions, okay? So to be a factor, your remainder has to be 0. In this case, it isn't. And the other thing that I've noticed that's sort of a recent phenomenon, I didn't notice this in my earlier years of teaching, but sometimes students take a remainder of 6 and they write 71.6. And I've never seen that until like the last, I don't know, 10, 12 years. The 6 is out of 11. The divisor here is 11, so it's 6/11ths. And that doesn't convert to 0.6. It would only be 0.6 if your divisor was 10. So that's just one of the things I wanted to point out. Now, anytime you do a division problem, you can check it with multiplication. Okay, so when a lot of people get stuck on this problem in the preview exercises, notice this original polynomial, this cubic polynomial, 2x cubed minus 3x squared minus 11x plus 6. If I divide it by the binomial x minus 3, this answer doesn't have any remainders. So what we say is that x minus 3 is a factor of this original polynomial because it divides into it evenly. It goes into it this many times. And so it's really not any different than if I gave you this problem. And I ask you to check this problem, you would say, oh, to check this problem, I take my answer and I multiply it by the number I divided by, and I get right back to where I started. Right back, the round trip, these are inverse operations, division and multiplication. It doesn't change with algebra. The idea is exactly the same. When you take 2x cubed minus 3x squared minus 11x plus 6 and you divide it by x minus 3, the answer, notice, has to be a quadratic trinomial. It has to be degree 2 because you're dividing a cubic by degree 1. So this answer has to be 1 less degree. And what that means is if you take this answer, 2x squared plus 3x minus 2, and you multiply it by the quantity you divided by, x minus 3, you have now factored this. You've taken this polynomial, which is just a bunch of terms, add, addition, and subtraction, pieces of adding and subtracting, and you've made it into a multiplication problem. That means you have factored it. Your instructions say to factor it completely. When you see completely, that means prime factors only. That's what completely means. Well, x minus 3 is prime. Can't factor that anymore. 2x squared plus 3x minus 2 may be prime, but you've got to check out some possibilities. So all you know is you're looking for factors of 2 and 2, Well, the good news here is 2 is a prime number, so it only has 2 factors. You're looking for factors of 2 and 2 that differ by 3. So right away, when I look at those combinations of numbers and I need to have them differ by 3, I think 2 times 2 gives me a 4, and 1 times 1 gives me a 1, and those two numbers differ by 3. I can factor this. So I use 2x times 1x and 2 and 1 plus and minus, and I have factored that. Okay. So the complete factorization is x minus 3, 2x minus 1, and x plus 2. That's the complete factorization of this third degree polynomial. Now, prior to doing this, you would not have had any methods that you've learned so far to factor this. You can't pull out a common factor of x. I saw some of you trying to do that because 6 doesn't have an x. So there's no common factor all the way through. Some people learned how to group things in pairs and find common factors. That doesn't work here either. Okay, so the only way to factor this is for some little birdie to come along and give you one of the factors, at least till the next 2 classes. You'll have ways of knowing after today's class and next class. But you already got one of your factors, and you got one of your other factors. Okay, so one of the things you're going to learn today is once you have the factorization of this, once you have the complete factorization, you can get a graph very quickly. Each one of these factors has a multiplicity of 1. So what are the zeros of this polynomial? What are the zeros? X equals what? What are the zeros? 3. How do I know it's 3? How do I know a 0 is 3? Because if I worked backwards, if I made this into a 0, I would subtract 3 from both sides, and voila, there's one of my factors. Okay, we're used to working from here. We usually factor something, and then to find the 0, we set the factor equal to 0, and we get our answer. Sometimes you might know what a 0 is. X equals 3 is a 0 of this polynomial. If I put 3 in here, I'm going to get 0. So x minus 3 is a factor that makes 3 a 0. 2x minus 1 is a factor to make it a 0. I get x equals 1/2. So I'm out here at 3. 0 is an x-intercept. 1/2, 0 is an x-intercept. And what's my last x-intercept? -2, 0. -2 being the 0. -2, 0 being my x-intercept. What's my y-intercept? 6. Woo, yes, the constant right there. Here we are, way up here is 6. All right. So to sketch this, I got everything I need to know right now to get a sketch. That's all I'm interested in, not accuracy, just a sketch. If I'm a cubic, what about my arm? Same direction, opposite. Oh, there I am, right? Right arm up because 2 is positive, the leading coefficient. So I know I'm going to end up here, and I'm going to begin down here somewhere. So to get this, I head for my 0. Oops. I'll probably be down here, head for my 0, come up above somewhere above my y-intercept, I don't know how high, go through my y-axis, come down, scoop back up. Okay, so there's a quick sketch of that third degree polynomial. Okay, and all I needed were my 3 zeros, my 3 x-intercepts, my y-intercept, and knowledge of my end behavior. That's all I needed to know to get a quick sketch. All right, so this is where we're going today. The division of 2 polynomials can be done with a long division algorithm very similar to the one we use for numbers. Okay, so let's take a look. We're going to have a little, I'm going to take the same problem we just did, but we're going to look at it from a place value standpoint. Okay, so I'm going to take 11 and I'm dividing it up into 110 and 1, 10 plus 1. I'm taking 700 and I'm dividing it into 7 hundredths plus 8 tens plus 7. So now when I do this division algorithm, where I start is with my biggest value, place value here. How many times does 10 go into 700? No, not 7, because that gives 70, right, okay. Oy, oy. All right, so 70. So where do I put my answer? I put it above my tens place, right there, 70, okay? So the first thing I do is say 10 goes into 770 times. I line up my like place values. Now, just like you did before, you take your answer and you multiply it by your divisor. So I take 70 and I multiply it by 10 plus 1, 11. But I'm going to do it in two pieces. 70 times 10 is 700. And 70 times 1 is 70, plus 70. So if we were doing this problem, if you look at your work in the preview exercises, you would have had 770 there. Or actually, you would have had just the number 77. But it was really 770. That's part of the problem with teaching division the way we do it, is that we lose track of our place value. So now I subtract 700 plus 70 from 700 plus 80. So to subtract it, since I have two pieces, I have to subtract both of them. I change the sign of both terms. 700 minus 700 is 0. And now I get 80, take away 70 is 10. And now I bring down my last place value here, which is 7 ones. So now I ask, how many times does 11 go into 17? And I look at my biggest place value, because that's what's going to help me. How many times does 10 go into 10? Once, and I put it right above my ones place in my quotient. And now I multiply 1 times 10 plus 1, and I get 10 plus 1. And now I have to subtract the 10, and I have to subtract the 1. 10 take away 10 goes to 0. And 7 take away 1 is 6, and that's my remainder. So my answer is 70 plus 1, with the remainder 6 over 10 plus 1. And with numbers, we combine that, and we say 71 with 6 11ths as the remainder. But if we kept it all written in its place values, that's what it would look like. So that's essentially what you were doing with the long division algorithm, but they shortcut it. Okay, and I think sometimes in the process of making a shortcut, you lose essentially what you're doing. I want to go back and remind you about some language for a second. The number you divide by is called the divisor. The number that's being divided is called the dividend. And the answer to any division problem is called the quotient. So anytime you do a division problem, you can always check by taking the quotient times the divisor and adding the remainder. And that will get you right back to your dividend. All right, so let's take a look at how we turn this arithmetic problem, which is what it is, into an algebra problem. So everywhere you see a 10, we're going to let x equal 10. So how would I rewrite this divisor right here? Instead of 10 plus 1, what would it become? X plus 1. Okay. So now it looks like algebra. It's x plus 1. 700 is 7 times 100. 100 is 10 squared. So 700 becomes 7 times 100, which is 7 times 10 squared, which using this substitution, x being 10, is 7x squared. So that's 7x squared right there. 80 is 8 times 10, so we write that as 8x plus 8x. And 7 ones, we could write as 7 times x to the 0 power, but why do that when we can just say 7? All right. So now I'm going to mimic the exact process I did on the left-hand side with the numbers with the algebra. So we started with our biggest place value with our divisor, which was 10. And now that's going to be equivalent to x. So I say, how many times does x go into 7x squared? So over on the side of my paper, I say 7x squared divided by x, 7x, because I subtract my exponents when I have like bases. And 7 divided by 1 is 7. So 7x. I need to put 7x above the like place. The like place here is my x place. So I put my 7x there. Just like I put my 70 over here. Then what did I do with my 70? I multiplied 70 times 10 plus 1, and now I multiply 7x times the divisor, x plus 1. So 7x times x plus 1 is 7x squared plus 7x. Notice 700 plus 70. That's exactly the same as what I have here. So I have 7x squared plus 7x. And now my job is to subtract both of those from the like terms above them, the like place values. So I subtract the 7x squared and I subtract the 7x. This gives me a 0, which makes me happy. And this gives me a negative 1x. I bring down my next place value. Oh, it gives me positive 1x. Thank you. All right, so now I say, how many times does x go into x? And what's my answer? Once. So I put a plus 1 right up here in the ones column. And I get 1 times x plus 1 is x plus 1. I change the signs on both of those terms because I'm subtracting the whole shebang. So this becomes a subtraction and that becomes a subtraction. My x's go to 0. And I have my remainder 6. So to write my remainder, I would write 6 over x plus 1. Okay. So notice, take a few minutes and see if you can see the relationship. I chose this problem very strategically so you could see the relationship with the arithmetic and the relationship with the algebra. Does anybody have any questions before we go on about this process that we just did? Okay, and you can always check it. The divisor, 7x, the divisor is x plus 1 times 7x plus 1 plus your remainder of 6 should equal your dividend, 7x squared plus 8x plus 7. Well, let's check it out. 7x plus 1 times x plus 1 is 7x squared plus 1x plus 7x plus 1 plus 6. We combine like terms, 7x squared plus 8x plus 7 equals that. You're a happy camper. You know you did everything correctly. So in terms of division, x plus 1 is not a factor of this polynomial. It's not a factor because it has a remainder that's different than 0. Okay, if you come down here and your last step after you subtract, you get a 0, then you know you have 2 legitimate factors of your original polynomial expression. All right, so let's take a look at this again. We're going to take a little different look. Now, if you're really good at factoring, you can factor 6x squared plus 5x minus 6. In fact, let's do it so we know what our answer is ahead of time. We can factor this. 6x squared plus 5x minus 6. It's a little, no, you don't have to write it anywhere. So you know how to factor this based on the techniques you've learned so far. All right. The problem is we're going to be seeing cubics and things to the 4th and 5th power that we can't factor, like the cubic we had initially. So you're looking for factors of 6, which is a little bit harder to do than factors of 2, but not too much harder. You're looking for factors of 6 and 6 that differ by 5. So right away, this is really how quickly I do it. And it's not because I'm so smart, it's just because of experience and practice. And part of the problem that I notice with students in Math 107 is factoring is one of the weakest skills you come in with. So factoring is going to be critical for this section of the course. Factoring starts on page 64 in the prerequisite chapter, section 5. So go back and review some of it. If factoring's been difficult for you, let me know. Come see me. Come to the studio. I'll be glad to help you. Okay. But let me just show you when I see a problem like this. I'm looking for the factors of 6 that in some combination differ by 5. Now, I'm the only teacher that teaches it this way. Most teachers will say factors of 6 and -6 that add up to 5. That's how they teach you. But because you have a -6 here, you're adding two numbers with different signs, which is just like subtracting. So it's easier for me to find the combination, look, that differs by 5, 9 and 4. So I put 3x and 2x. The 3 multiplies the 3. The 2 multiplies the 2. And let's see, is that right? 4x and 9x. And I got to come up with a 5x. So that's minus and that's plus. And that's how quickly I factor. But I've been doing this for a while. But it's really one of those situations where, and you see, I already gave you one of the factors, 2x plus 3. So when we do this division, our answer should come out to be 3x minus 2. Okay, we're going to get 0 for a remainder because those are two factors of 6x squared plus 5x minus 6. So we know what our answer is before we go in. So let's make sure we do all the steps right. Now, the first thing you have to make sure when you do any kind of division problem is you line your polynomial up in descending orders of powers. Like if I gave you the number 179, you wouldn't write 719 or 971. You'd write 1 in the first in the 100 spot, 7 in the tens, and 9s in the ones. So you got to make sure everything's in descending powers. And in both of these situations, they're all set. They're in descending order. Okay, so that's done. Now you just take a deep breath. And you write out your division problem like you would if it was two numbers that you were dividing. And you start with your largest place. In this case, we call it the largest power. Here we have 2x to the first power. So I say, how many times does 2x go into 6x squared? And on the side of my paper, I do a little work like this. 6x squared divided by 2x gives me 6 divided by 2 is 3. X squared divided by x is x. So I say 3x, and I know I've got to put it in the right column, the right place value above the like term, however you want to think of it. And now I say 3x times 2x plus 3. 3x times 2x plus 3 gives me 6x squared plus 9x. 6x squared plus 9x, and I write that just below here. And now I have to subtract both of them. Change the signs of both terms. So that becomes a minus and that becomes a minus. That goes, oops, that should be 6x squared there. So that becomes the 0. 5x, take away 9x gives me negative 4x. I bring down my next place, minus 6. And now I ask myself, how many times does 2x go into negative 4x? So on the side of my paper, I have 2x into negative 4x. Negative 4 divided by a positive 2 is a negative 2. X divided by x gives me 1, so my answer is minus 2. Or put it right there. And now I do negative 2 times my divisor, 2x plus 3. Negative 2 times 2x is negative 4x. And negative 2 times 3 is minus 6. So now I do negative 4x minus 6. The minute you see that, you want to jump for joy because look, these are identical. So when you subtract two identical things, you know you come out to be 0. You change the sign, and you get a nice big happy 0. And these are your two factors of the original polynomial. Okay. So had we said that this was our function, just so you can see where we're going, folks, if this was our original function, a quadratic function, you would factor it. And why do you factor it? To find the zeros of the function. Because once you find the zeros of the function, you know its x-intercepts. Okay. All right. So that's the long way to divide. Now your book is going to teach you something called synthetic division. I don't teach synthetic division. Some students like it better because you don't have any of your x squares and x's or any of that. You just have the numbers. I just want to caution you. Just if you came out of math 096 and you learned to factor this type of quadratic trinomial with the box, doing this kind of thing, versus understanding what factoring is, the minute you stop doing it for a while, it's gone. Because it's just some little, I mean, it's a nice thing. It's a nice thing that our book does to show you, because sometimes students need a little structure to factoring. But the minute they have a summer in between or whatever, they don't remember the box. They remember the box, but they don't know what goes where and how they get it. As opposed to knowing that this has to be two factors. We know something about these factors and the numbers that go in there. And the problem is factoring takes time. And we don't like anything that takes time, because everything comes to us like this. We can go halfway around the world in 100th of a second. Okay, so we've become an impatient generation, and factoring takes time. The same is true with the difference between long division and synthetic. It's a little quicker for sure, but the minute you stop doing it, you'll never remember it. So I'm not going to tell you what to do. And on a test, if I ask you to find factors of a polynomial and I ask you to divide, you can do either one you want. It's really fine with me. I'm just suggesting that it wouldn't be bad to have both of them down, and then you have a check for yourself. But, you know, life is short, so do whatever you need to do. This is where it all comes together, folks, on the next page, number 3 and 4. Fact number 4, anytime you see the word theorem, you know it's important. This is a major idea right here, so put all big stars, whatever you want to do, happy faces, I don't know, whatever you do to make something look important to you. You might want to write it on your phone or something if that makes it important. All right. This is going to be our major idea for taking all the stuff that we're doing today and over the last couple of days and pushing it together. The idea that if you know a factor, you know a zero. And of course, what goes along with that is if you know a factor of a polynomial, you know a zero of a polynomial function. So I just shortcut it a little bit. If you know a zero, and then it goes the other way. If you know a zero, you know a factor. And of course, the word zeros and x-intercepts and factors, they all start to meld now and come together. So here I said, suppose that a polynomial function f has these 3 zeros. Notice how I list zeros. They're individual values for x. They're not coordinates of a point. Those are x-intercepts. But we can turn each one of these into x-intercepts when we graph. So here are zeros. When you look at your graph, which happens to be provided for you, you see the corresponding x-intercepts that are associated with those zeros. Okay. Now, what you're not used to is when you say x equals 1 is a zero of the function, you want to go back one step. We're used to going from the factor to the value for the zero, but now we have the zero. the value of the 0, and we want to go back to the factor. So what would I have to do to both sides of this equation to make it look like an equivalent equation with 0 on the right-hand side? What would I do? What would be my step? Subtract the 1 from both sides. If I subtract 1 from both sides, I get x take away 1 equals 0. This is the form we're used to dealing with. We usually have something like this, right? We have a factor, and then we solve it for 0, and we get x equals 1. Now we're going to start with the 0, and we go back one step. So I look here, and I see that 0, so I know one of my factors is x take away 1 for my polynomial. I know it goes straight through, crosses. It has to have an odd multiplicity. But since it goes straight through, it looks just like a line, so my multiplicity is 1. You can either write it there or not. It's up to you. Now I look at my 0 of 3. If x equals 3 and I know it's a 0, then I can rewrite this equation so that it has 0 on the right-hand side. And to do that, I subtract 3 from both sides. There's one of my other factors. To the first power, because it goes straight through, it crosses. My function changes sign. It was below my x-axis, and now it's above. I know it's an odd multiplicity. Yeah, I'm getting there. I'm saving that for last. All right. Now, let me erase this because I always run out of room because I write so big. The other 0 I have is x equals -2. I know that's a 0. So I want to step it back one step to see what my factor would have looked like to give me -2 as a 0. So what would I do to both sides here to make this top equation? Add 2 to both sides, x plus 2. So when your 0 is negative, it always will have the x minus form, because x minus a -2 simplifies to x plus 2. So when your 0 is negative, when your 0 is a negative number, subtracting a negative becomes adding the positive. And again, it has multiplicity 1. We do not know what the leading coefficient is. So if I asked you for a possible equation for this particular graph, you would say, I know it's odd. My right hand is up, so my A is positive. You could tell me that. Notice you have 3 zeros, all with multiplicity 1. You have 3 linear factors. 3 linear factors. Why do I say 3 linear factors? Why do I use the word linear to describe those factors? Yep, Bridget? Yeah, we know it looks like a line. It has multiplicity of 1, right? So the highest power you see is x to the first, okay? Because it crosses straight through. All right, so this is all you can tell me about this graph right now. If I had a little point on here and I told you what the coordinates were of that point, other than the zeros, you could take the x value and plug it in for x, and you could take the y value and plug it in for f of x, and you could solve for a. But we don't know any other point on this graph right now. Christine? If you knew it, we can't see it. You see, we can't solve for the y-intercept right now because all we know is x is 0. We don't know the value of y, and we don't know the value of a. So there's 2 unknowns. You know it's close, it's a little bit more than 5. But if it went right through 0, 5, then we could put 0 in here, and we'd have 2 times -1 times -3, and we'd have a 5 here, and then you could solve for a. It would be a fraction. But, you know, did I say that right? 2 times -1 times, it would be 6/5, right? 5, 6. If it was 0, 5. If it went through 0, 5, we could find the value of a. But we don't know. But all we can say is a is positive because your right arm is up. That's all you know. Again, remember, in factored form, when you have something in completely factored form, you can tell the degree by adding the exponents. 1 plus 1 plus 1 tells you it's a third degree. You also know it's a third degree because you have two relative maxes and mins, and when you solve that for n, you get 3. So this is like putting everything together that we've learned. Okay, so if you know the zeros of a polynomial with their multiplicities, then what are the factors of the function? Okay, so if x plus 2 is a factor of the function, then f of negative 2 is a 0. If x minus 1 is a factor, then f of what is a 0? Positive 1, right? Because if I put a 1 right in there, I get 0. If x minus 3 is a factor, then f of what is 0? 3. Now vice versa. If f of negative 2 is a 0, if you know a 0, you know a factor. Because x take away a negative 2 becomes x plus 2. If 1 is a 0, then you just say x minus 1 is a factor. If 3 is a 0, then x minus 3 is a factor. So if you know one of these, you know the other. And that's exactly what this factor theorem tells you. So let's use this factor theorem to do number 5, and then you'll have time to work on your problems and your class activities. So here's a long cubic. Have you seen this before? Yeah, this was in your preview exercises. Okay, you don't know how to factor that right now. Well, you kind of do because we did it in the preview exercises, but let's make believe we didn't. I gave you the answer in the preview exercises. So there's a cubic. It has all 4 terms. There's no common factors. You can't possibly factor this right now until someone tells you something about that polynomial. They either have to tell you one of the factors, like you did in the preview exercises, or someone has to tell you a 0. And I'm telling you right now that negative 2 is a 0. So by the factor theorem, if negative 2 is a 0, then what is the factor going to look like for this polynomial, one of the factors? X plus 2. So now you can find your other factors by taking 2x cubed minus 3x squared minus 11x plus 6 and dividing it by x plus 2. What should you expect for a remainder? What should be the remainder when you're done? 0. How do you know? How do you know it's 0? Because it's a factor. Exactly. All right, so when I did this in my last class and I was walking around, someone said, you did that so fast, I need you to do it all over again with me. So I'm not going to do it. I'm going to ask you to tell me what to do as the first step. So that way it will slow me down. Right, divide 2x cubed, which is your first term, by x. So off on the side of my paper, I take 2x cubed, and so this is step 1. I divide it by x, I get 2x squared. One of the things we neglected to say is to make sure you're in descending powers. What happens if I get something that doesn't have an x? What do I put in there? I leave it blank? 0x. You've got to put zeros in each place value, just like you do with numbers. So if you had something that didn't have a term to a power of 1 or 2 or 3, you put 0 as the coefficient. You need to hold the place value. All right, so x goes into 2x squared, 2x cubed, 2x squared times. I write it above my x squared place value. There we go. My like term. Now what do I do? Someone other than Carlton. You're turned off, Carlton. CP's done. Ben? Yeah. Right, I multiply it by my dividend, and what does that give me, Ben? Yep. Okay, So I write my 2x cubed plus my 4x squared here. Now what do I do? Someone else, step 3? Switch the signs, which means I subtract both of them. So I subtract 2x cubed and I subtract 4x squared, and that means I change both signs. There they go. 2x cubed minus 2x cubed is 0. 3x squared take away 4x squared is, nope, negative 7x squared. And I bring down my next term. Okay, so I subtract and bring down negative 11x. All right, almost done. I only have 2 more divisions to do. What's my next step? I think you already helped me, Josh, with the negative 7x squared, so you're done. I'm going to put Josh right here, JS. Okay. Divide negative 7x squared by x. And what does that give us, Mackenzie? Negative 7x. So where do I put the negative 7x? James, can you help me? Over the negative 11x, right? I put negative 7x. All right. And now step 6 would be what, Bridget? Whatever it's called, the divisor. Okay, and what would that give us, Bridget? Negative 7x squared minus 14x. Okay, and I'll put that right up here. And who wants the next step? Shannon, how about you? Right, I have to subtract. So I have to change that to plus and that to plus, and it gives me 3x. And then I bring down the 6. Okay. Whew, almost done. X goes into 3x. Ta-da! How many times? 3. And when you multiply 3 times x plus 2, you get 3x plus 6, and you're a happy camper, because when you subtract 3x plus 6 from 3x, you get a big fat 0. So you have factored this, but not completely. You have found 2 of the factors, and now it's the step we went through in the preview exercises to finish it off. And there you go, it's done. All right, so that's long division. You have very different class activities. I'd like you to look them over. If you need work on the skill part of today's class, which is a long division, you want to start with number 1. If you'd rather be a little more challenged and try to come up with equations for a graph by looking at multiplicities and zeros, and you'd want to move along to like 3 and 4, start wherever you feel like you need the most help and while you have resources available to you in class, okay?